Okay, so we're going to start in spite of people wandering in and out. My name is Jeff Weekly. I'm a research associate here at the Naval Postgraduate School with the Moose Institute. I am very pleased to be here today to talk to you with this gentleman, and I'll let him introduce himself, and then we'll get started.
My name is Jeff Hofferman, and I'm the Director of Research Computing here at NPS. And this is a very interesting project because Jeff and I had to basically take our skill sets and merge them together. So
Worlds collide.
Yes, worlds have collided here. So I've worked for a long time in the area of supercomputing, and Jeff has worked a long time in the area of visualization. So we worked together in this presentation, and so we're going to tag team here.
So thanks, Jeff. And so if you have a question for one of us, you can just say Jeff. It works. So what we're going to talk to you about today is the way for you to bring to bear some of the computing assets that you may have on campus in ways that you might not have considered before. And these are not new techniques. We are not pioneers here. We do feel a little bit like trailblazers here at the Navy School, but really these are things that have been applied in many areas, and we'll show some of those things here coming up. Here's our agenda. First, we're going to tell you a little bit about our supercomputer, and I got a chuckle out of Dr. Van Beber's description, our small supercomputer. I guess that's true. Seems like a rocket ship to me. We're going to talk about what is Renderman, and this needs clarification, and we'll get into that. We'll talk about a survey of our software and tools. We'll show you some pretty pictures and have some results for you. So this first slide's Jeff, and I'll let him address that. So
I'm not going to talk a lot about this, but a little over a year ago, we procured what's called a Sunblade 6048 system. And this is just a picture of front and back of a single rack. We have 4 of these racks, so a total of 152 cores, basically processors, and a peak capability of 10.7 teraflops. So the previous speaker started talking about petaflops, which is 1,000 teraflops. Today, a petaflop machine is sort of the most powerful. So we're about 100 times less powerful than the most powerful computer in the world. But that's still 10.7 trillion floating operations per second. And this, again, was manufactured by Sun. And on some of the nodes, we have an InfiniBand interconnect, which is a 20 gigabit per second communication channel that connects the blade servers to one another. This really gets into the guts of one of these blades. Each has an Intel Xeon CPU with dual quad cores, so 8 cores, clock speed of 2.33 gigahertz, 8 gigabytes of RAM, and multiply this by 144, and that gives you the system that we're working with. So we're running, just for those of you who are interested in this sort of thing, CentOS 5.2, ROX 5.1, and Sun Grid Engine as our batch scheduling system. In terms of network storage, we have something called Data Direct Networks. Can do very fast I/O, capable of doing 5 gigabytes per second reads and writes. We have 100 terabytes usable. In this one cabinet, we can expand up to 1.2 petabytes. And this is also connected to our system via InfiniBand. So again, this allows us to do very, very fast input-output.
So that's a little bit about our infrastructure. Now I'm going to talk about what is Renderman. Renderman is many things. In fact, I chide the people up at Pixar when I'm trying to figure out how their software works. I'm like, it's the Renderman of the, and they're, well, everything's named Renderman. In this case, we'll be talking about the Renderman interface specification, aka the Renderman API. and several software packages that use Renderman's algorithms to do photorealistic rendering. And that is using a computer to generate an image. So that's what I mean when I say rendering. First published in 1988, Renderman includes ways to describe geometry implicitly, which means you don't have to specify every point to build something. It also includes a shading language, what do things look like? And this allows you to apply sophisticated appearances to the geometry that you may have specified. And it all runs in this thing called the Reyes algorithm, and we'll talk a little bit more about that. So the software that we surveyed sort of comes in two flavors. The first kind works with Maya, and Maya is a commercial software package. I talked about it a little last year in my talk, that you use to do 3D modeling and build visualizations and simulations. 3D Delight is a package that works as a plug-in, same as Pixar's Renderman. And then Pixie is an open source command line or script only. The first two, Renderman and 3D Delight, work as a plug-in to Maya or script and command line, and the last one is command line or script only. So a little bit of nomenclature for the non-computer scientists out there. An API is an application programming interface. It's sort of the glue that holds two pieces of software together. And in this case, Renderman is the API for doing 3D modeling, hooking those up to the rendering programs. So if I were to put this in plain language, I would say that a 3D modeling program can speak Renderman, and the 3D rendering application understands what it's saying. So this is just a short little vignette that I put together to give you an idea of what the end process there looks like. So you see specular highlights, you see reflections, you see shadows, you see depth of field, all the things that you would see if this were a real photograph. And that is the famous Pixar teapot. And it's specified in such a way to make it very easy to access. So how these pieces of software talk to each other is called the RIB file, or the Renderman Interchange Binary file. And I have an example of one over here. I don't expect you to read it. I did call out that number 24 right there. And if you take a look at that, that line says projection, perspective, FOV. And FOV means field of view. That means how much can you see in the frame, right? So when you're zooming your camera in and out, you're really changing your field of view. And in this case, I'm going to change it, the 24 to a 72. I am zooming out. And if you do this, you can move your camera, you can move the objects in the 3D scene in such a way that you actually can end up creating a 3D movie. And we'll talk about that a little bit later. I'm going to hand it back over to Jeff, and he's going to talk about how we distribute these tasks in our architecture.
So when we're doing rendering, it can be a very computationally intensive process, and there are a couple ways to think about this. We have all these nodes in our supercomputer, as I mentioned, 144 nodes, over 1,100 processors, and we can break these rendering problems up into, we can hand off each node and ask it to render a frame in our image, or we can ask the nodes to collaboratively work together and work on a single frame. So either way is acceptable. So we have a master process that kicks it off, that work on several data sets, slave processes, and everything finally has to be written to disk. Let's go to the next slide. We're using something called Sun Grid Engine, and I just want to mention that because this is a freely available piece of software that allows your tasks to be distributed among nodes and even across various architectures if you want to. So in this figure that I've shown here, you could use a Spark chip. You could use an AMD chip, an Intel chip, have several different types of computers, and with the Sun Grid Engine, you can divvy up the tasks among all these architectures to work on a single problem. So that's where I come in, getting this stuff to work and interface with the Renderman software. Next slide. Yes.
Do you use a parallel file system? What's the file system?
We're using the Lustre file system, which yes. So it's a very fast file system, and yes, it's
and that's across
system.
all the applications.
And the interconnect between the different nodes?
It's InfiniBand.
It is InfiniBand.
Yes. Not on the entire cluster, but on about 30% of the cluster. So for the rendering that we did experiments on both the InfiniBand interconnect and the gigabit Ethernet.
But it's interesting to note that really the files, the data that we're loading on these nodes for tasking are those RIB files, and they can be very lightweight. Now what they produce is maybe a very large pixel by pixel image with lots of data, but sending the RIB files out is really sometimes no more than a text file.
Okay, so Jeff had mentioned earlier the RAISE algorithm, and RAISE stands for what I have up at the top here, renders everything you ever saw. So I just want to get people familiar with this nomenclature. I'm new at this stuff. Like I said, I know the supercomputing end of it. Jeff has been around this jargon for quite a long time, and so I had to get myself up to speed by it. But it's used, RAISE algorithm is used by the three pieces of software we use. Renderman, which is proprietary software, Pixie, which is free, and 3D Delight, which is proprietary. Essentially, RAISE dices all the geometry into tiny polygons at render time, and you can also do shading. That's part of RAISE, and that minimizes the time fetching textures. There's very minimal ray tracing that goes on. Ray tracing can be a very, very computationally intensive problem, and RAISE minimizes that. And as the distance to the viewer increases, fewer polygons can be used with little loss in quality. So RAISE takes advantage of that to render things efficiently.
And in graphics parlance, that's called level of detail.
The Newell teapot. So
how many people know of the teapot? So we have some people who know of the teapot. Probably
Okay.
been to SIGGRAPH.
Yes. So Martin Newell, University of Utah, in 1974, was trying to do some visualization, and as the story goes, apparently saw the Melita teapot in his kitchen and said, well, I think I'll use that. That's the actual teapot in the center. It's now in the Computer History Museum, just up the road. But just to show a couple different renderings here of this teapot that people have used, and an example of a way that this is described in this Renderman interface binary language, a RIB file. Next slide.
Meow.
Meow. Here we go. Cat as polygons. So earlier I was talking about as you get further and further away from an object such as this, the polygons, the number of polygons matter less. So if you're a far ways away from the cat on the right, you're not going to see those little polygons, but as you zoom in, you will start to see them. So a lot of this rendering depends on how close you are to the object and how much refinement needs to be done on these polygons. So if we're going to really zoom in on an object such as this, the rendering time takes much, much longer to continually refine these polygons. Multi-pass rendering, this is something the RAISE algorithm also does. So I've just shown up here on the left, upper left, RAISE algorithm can produce shadows, and on the upper right, a diffuse image without shadows. And this is actually the combination of those two. When the RAISE algorithm combines the two objects, renderings on the top, you get this combined image. And finally, you can add specularity or shininess.
It's very noticeable here in the corner. This is flat. There's no shadow there. Here you see the shadow, and when you combine them, you really get the depth, and it looks a lot more realistic. That's why all of these elements in combination are much more compelling than any single element on its own. So I have an example of this that's a little bit more complex than that one, and indulge me because it took me a really long time to put this together. So it's well suited for parallel processing. Each pass can be managed from a single or multiple RIB files. You can composite later. It's possibly a supercomputing function. Send it to a nonlinear editing system making movies, or send it to a visualization system for cluster-by-cluster rendering. So here we are, and you probably can't see it because the door is open. Natalie, could you pull the door shut? Some of the elements of these images are quite faint. This is occlusion direct area light. We have occlusion direct, specular direct. This would be the shininess. We have the diffuse color, the specular direct, and there's just a little thing there. It looks like a smudge on the screen. And this is the final pass. So combining all those elements together and then putting in a background plate with compositing, this is the image that you get. Very nice. Okay? And this is an example rendered in Pixar's Renderman. I didn't do any of the 3D modeling. It's just an example. What I did was break out the passes one by one, render the images, and the composite. So if you think about each frame, and for movies we look at them 24 frames per second. Some of the stuff we'll be showing you later is 60 frames per second. Each one of those frames is rendered, and then they're put in a sequence, and you play it back, and you get a little movie. And you do this about how many times, Jeff? Well, I guess we'll get to that.
We'll get to that. We have a slide on that. Yeah, it's right here. So here's an example. I don't know how many of you saw Ratatouille. Okay, a lot of you. And how many of you watched the Oscars last night? So there's
three people.
3 people watched the Oscars. But Up is another example of a film that required heavy-duty rendering. But Ratatouille was a Disney Pixar film produced in 2007. Pixar used 850 servers, and it's interesting. I discovered Pixar, is an offshoot from Steve Jobs and Apple, and I found out that they're using Dell servers, which is kind of interesting. But 850 servers, 3,200 cores, and a statistic I read that to produce a single frame for this movie takes 6 hours on a single core. So that's 6 hours for one frame. The movie has 24 frames per second. It's an 111-minute movie. That means there are about 1 million renders that had to be done for that movie. So that's 6 million CPU hours. So taking that machine, if they were just to go at it full blow, and I'm sure they had to re-render and do things over and over, but if you could start from time zero and render that entire movie, it would take 78 days on that computer just going full time to render this movie. And Ratatouille was done using the Renderman software. Now, what Jeff and I are going to show you, some of the things, it's not going to look like Ratatouille. Otherwise, we'd be working for Disney and Pixar and getting an Oscar. So we started out with some very basic stuff. We started out with the Newell teapot and Renderman and the different software that we have. So here you go. Here's our teapot. This is actually where we started out. We had to start from ground zero, again, using these different brands of software, Renderman, Pixie, 3Delight. We experimented with multi-thread, multi-core. We did have some license issues. Renderman is a commercial product. 3Delight is a commercial product. And we used other images as well, which I'll show you on the next slide. But this really served as our benchmark, just rendering this over and over and over again using the different software and, again, experimenting with the multi-thread, multi-core, doing timing, seeing what worked well. Next slide. Here are some of our other, I'll call teapots, even though this is not a teapot, this is a spiral, but it's something that worked very, very well for doing benchmarking. Some other teapots down here, you can see the reflection, the specular reflection, multiple teapots, that sort of thing. These are, depending on the resolution and your field of view and all the other parameters, these can render very quickly, or they can take a long time if you want to actually zoom in on some of these objects and not see that granularity. Let's go to the next slide. Here are just some initial findings, what we found. And just for those of you who are interested in getting into this, a single Renderman license, which costs about $2,250 for academic use, licenses a single machine, a single core on a single machine. So the rendering works great, but if we wanted to scale this to a large render farm, it would be very, very expensive. Pixie, on the other hand, which is free software, and it's out there for your use, supports multi-thread and multi-node, but it doesn't support all of the rib attributes, and the render quality is not as good as Renderman. So all of these, 3D Delight included, its license was about $300 for an academic use. It supports multi-threading and multi-node, and it supports most rib attributes. So for the work that we were doing, the 3D Delight really seemed to be the best option. So all of these, Jeff was talking about the Renderman API earlier. All of these support the Renderman API.
So what's interesting about this discovery process is that they're all Renderman compliant, but that's a relatively short list of functionality. And so we found that that short list, which Pixie certainly satisfies, isn't going to give us enough flexibility to do some of the more complicated things like volume renderings and clouds and complex shapes. So Renderman from Pixar is great. It's a very sturdy plugin. It's a well-supported tool. There's a lot of people out there using it, and you can get just a Renderman plugin for Maya for not much money. We chose the enterprise grade and got a great discount, but it still won't scale up to a large computer. So I like our approach, which is buy one or two of the Pixar Renderman licenses, because you can use that to make your rib files, and then get a free or a low-cost license to actually do the rendering. So there's two things here. There's the file creation, which works 3D Delight and Renderman as a plug-in to Maya, and then there's the actual rendering. So that's our architecture. We use 3D Delight and Maya, or Renderman for Maya, to create the files, and 3D Delight and Pixie to render them.
Okay, so this is, I think this is our consensus, but Jeff can tell me if it's not. But I think we pretty much settled that Renderman is the best, and it's the original, but it's expensive. We couldn't afford a multi-core license. We'll look into that in the future. So we couldn't test Renderman with SunGrid Engine. Pixar provides a very nice suite of tools for rendering, shaders, and scheduling, but these tools have not yet been integrated into SunGrid Engine. Pixie and 3D Delight, on the other hand, integrate very well with SunGrid Engine and therefore with our infrastructure and our supercomputer. 3D Delight also has a tiling option that allows the rendering engine to learn and to accelerate rendering times, which is very cool because when you're rendering these scenes, you will actually see that as you start to render scenes over and over and over again, it accelerates as it goes along.
So it's load balancing and spending less effort on areas that require less rendering to them. So we did a couple little tests, and that was pretty cool. That was unexpected.
And this is our summary slide. This is our initial foray into rendering on a supercomputer. And again, there's a very steep learning curve from somebody like me, who I'm very well versed in using computers, but I haven't done a whole lot of work in visualization as Jeff has. So just to go from zero knowledge to rendering teapots, for me, was a big deal. And like I said, when we go to Ratatouille, we're probably going to take off and just go down to Hollywood for that. So, but this technology has largely been driven by the movie and gaming industry for DoD visualization needs, of which there are many, such as virtual reality and augmented reality. We're going to continue down this path and continue to really develop this kind of framework on our supercomputer. There's much promise also with state-of-the-art GPUs, graphical processing units. Right now that's mostly NVIDIA, AMD, ATI, and Intel has talked about their Larrabee chip, which should be out soon, which is a hybrid graphical processing unit and a traditional CPU. So I think if you look at where this technology is heading, and again, being driven by movie and gaming industry, and our earlier presenter talked about Moore's Law, in order to keep up with what Moore's Law said where we should be every year, this exponential increase in computational capability, technology such as GPUs and hybrid GPU, CPU, I think that's where things are headed right now, and that's what you're going to see in the next year to two.
So I would add one more impromptu bullet to this slide. I would say that you can do this on your laptop, but you can do this on a supercomputer a lot faster. So many thanks to our collaborators and supporters and all the people we work with. I have a really fun job. So thank you for your attention. And we will end 1 minute early, so I guess we have time for questions.